engine and fuel system. In this video, the following topics will be covered: engine, fuel system, carburetor, engine. The aircraft is powered by a Rotax 912S2 engine featuring 4 horizontally opposed cylinders, liquid-cooled cylinder heads, and ram air-cooled cylinders. The engine is equipped with 2 carburators, an integrated reduction gearbox with a torsional shock absorber, and an overload clutch. The propeller is manufactured by GT Propellers and consists of a one-piece, 2-blade, fixed-pitch, tractor-type propeller constructed of wood with a protective laminate coating. The engine is isolated from the rest of the aircraft by a 0.4 mm of thick stainless steel firewall. It is supported by a steel engine mount assembly attached to the firewall. This assembly consists of a steel truss and an engine suspension frame. The engine is mounted on 2 shock mounts that use rubber absorbers to isolate the airframe from engine vibrations. The engine is enclosed in a cowling divided into 2 parts, an upper cowling and a lower cowling. Access doors can be easily opened by releasing 4 latches, 2 on each side, allowing the pilot to perform pre-flight and daily inspections. Air circulation is ensured by frontal openings in the nose section and an outflow area located on the lower cowling near the firewall. Ignition system. There are 2 independent ignition circuits located in the engine compartment. Both are controlled by the ignition key, which is positioned on the lower left-hand side of the instrument panel. The ignition key has 5 positions: off, left, right, both, start. The magnetos are completely independent and can be operated individually, left or right positions, or simultaneously, both position. The engine requires battery power only for the initial startup. Once the engine is running, the ignition system is self-sustained by an internal generator integrated within the engine, and it does not depend on the battery or the external alternator to continue operating correctly. If the engine is running and both the master and generator switches are accidentally turned off, or in the event of a total electrical system failure, engine operation will remain unaffected. The ignition boxes are located in the engine compartment upper side, between the carburators. They are located in such a way that they are not in contact with flammable fluids or vapors. Liquid cooling system. The liquid cooling system is a closed circuit equipped with an overflow bottle and an expansion tank. Coolant flow is driven by a water pump operated by the camshaft, circulating coolant from the radiator to the cylinder heads and then to the expansion tank. The expansion tank is sealed with a pressure cap fitted with both a pressure relief valve and a return valve. When the coolant temperature rises and expands, the pressure relief valve opens, allowing coolant to flow through a hose into the transparent overflow bottle at atmospheric pressure. As the system cools down, the coolant is drawn back into the circuit. The radiator is located at the front of the engine cowling, attached to the engine mount. A cylinder head temperature (CHT) sensor, along with its corresponding instrument located on the right side of the instrument panel, completes the system. The CHT provides an indirect indication of the coolant temperature. The thermostatic valve, equipped with 2 thermal sensors, automatically regulates the coolant temperature by controlling the coolant flow to the radiator, maintaining it between 50 degrees C and 135 degrees C, green arc on the CHT indicator. The thermostatic valve operates in 3 different modes depending on the detected temperature. Coolant temperature below 90 degrees Celsius. The scheme shows coolant flow at T-90 degrees Celsius. The coolant in the overflow bottle is sucked into the circuit. Before reaching the pump, the coolant passes through the thermostatic valve, whose thermal sensors at temperatures below 90 degrees Celsius deny access to the radiator. Once it reaches the pump, the coolant is transferred to the cooling circuit and then to the overflow bottle. Coolant temperature between 90 degrees Celsius and 100 degrees Celsius. As in the previous case, the coolant is forced by the pressure generated by the pump. But in this case, due to thermal expansion, the first sensor set to 90 degrees Celsius is pushed down. In this configuration, part of the coolant is directed through the radiator. Coolant temperature above 100 degrees Celsius. Both thermal sensors of the thermostatic valve are pushed down, and all coolant flow is forced through the radiator. Exhaust. The exhaust system is made of stainless steel and consists of a muffler and exhaust manifolds. The temperature of the exhaust gases is monitored by EGT, exhaust gas temperature, probes installed on each exhaust manifold. The EGT indication is displayed on the G3X system. Through the heat exchanger, which is connected to the muffler and riveted to the exhaust rings, ram air is heated and then directed to the cabin heating and defrost system. Oil system. The aircraft is equipped with an independent oil system designed to supply the engine with the proper quantity of oil, maintaining the temperature within safe limits for continuous operation. The engine uses a dry sump forced lubrication system featuring a main oil pump with an integrated pressure regulator and oil pressure sensor. The oil pump draws oil from the oil tank through the oil cooler and then forces it through the oil filter to the designated lubrication points. The main components of the oil system are oil tank, oil quantity measurement device, dipstick, thermostatic valve, oil radiator. The oil system of the aircraft also includes the following additional components located on the instrument panel: oil temperature sensor, oil pressure sensor. The thermostatic valve regulates the oil flow to the heat exchanger, oil radiator, allowing the oil to follow two different paths depending on its temperature. When the engine is cold, the valve limits the flow to the radiator, enabling a faster engine warm-up. The same behavior occurs under cold outside air temperature, OAT conditions. As the oil temperature increases, the valve progressively allows a greater flow through the radiator. Oil temperature below 90 degrees Celsius. The oil contained in the tank is sucked from the oil pump, which pressurizes the circuit. The oil is then routed through the thermostatic valve, which is fitted with two thermal sensors, allowing for a partial radiator passage occlusion for temperature below 90 degrees Celsius. Once came to the pump, oil is transferred to the engine lubrication circuit and then to the cartridge filtering element integrated in the engine. The oil is then piped in the oil tank. Oil temperature between 90 and 100 degrees Celsius. As described above, the pump circulates the oil, but in this case, the first thermal sensor, set to 90 degrees Celsius, allows the oil to pass through the radiator where it is cooled. The cooled oil then mixes with the remaining oil before reaching the engine crankcase, where it is filtered. Finally, the oil is collected in the oil tank. Oil temperature greater than 100 degrees Celsius. The schematic shows the oil circulation when the oil temperature reaches or exceeds 100 degrees Celsius. In this condition, due to the activation of the second thermal sensor, the entire oil flow is directed toward the radiator for maximum cooling efficiency. The oil system is equipped with an oil filter, cartridge type, designed for full-flow oil system in order to filter the contaminants from the circulated oil before it passes through the bearing surfaces. The oil radiator is installed on the front end of the engine cowling and it is connected on the engine mounting. The oil tank is installed on the firewall protected from heat sources. It has a capacity of maximum 3 and minimum 2.5 litres. On the upper part of the oil tank, there is a dipstick to control the oil quantity. A vent hose, immediately located below the filler cap, allows for oil relief discharged in a safe zone in the cowling, far from exhausts and other heat sources. Fuel system. The system is equipped with 2 aluminum fuel tanks integrated within the wing box and accessible for inspection through dedicated access doors. Each tank has a capacity of 62 litres for a total capacity of 124 litres. The unusable fuel amounts to 1.35 litres per tank. In the outside area of the tank, there is a vent connected to wing tip hole that allows the discharge of the overpressure gas. The tank cap is positioned on the top of the wing and is easily accessible from the leading edge of the aircraft. In the central area of the tank, there is also the fuel level sensor, which, through an electric cable, transfers the reading performed by means of a float to a level indicator located on the dashboard. As shown in the following figure, each tank is provided with an area of expansion equal to 2% of the entire volume, about 1 litre. The compartments of the wing box and the leading edge adjacent to tanks are ventilated and drained through a series of holes. Under normal operating conditions, fuel is drawn and filtered through a suction pipe filter connected to the tank's suction system. A fuel selector valve allows the pilot to choose between the left and right fuel tanks or to shut off the entire system. From the suction system, the fuel is drawn through the electric pump, where it is filtered again. From the electric pump, the fuel is sent to the gascolator, which provides a third and final filtration stage before being sucked by the main mechanical pump. All fuel lines inside the engine compartment are flexible hoses, while those from the tanks to the firewall are stainless steel. The electric fuel pump serves as a backup, supplying fuel in case of main pump failure. Carburetor. The Rotax engine installed on the Technam is equipped with 2 carburetors. Carburetors are devices used in aircraft engines to mix air and fuel just before combustion. Each carburetor supplies the mixture to 1 bank of cylinders. The type of carburetor installed is called a constant depression carburetor. It is designed to maintain a nearly constant pressure drop inside the venturi, which ensures a stable and accurate fuel-air mixture across different engine power settings. By moving the power lever forward, you open a throttle valve. This allows more air and more fuel to enter the engine, increasing the power output. By moving the power lever back, you obtain the opposite effect. When the outside temperature is cold and the engine is not yet warm, a richer mixture is required for starting. That is, more fuel is needed to get the engine running. For this reason, the engine is equipped with a choke. When the pilot activates the choke, additional fuel is delivered into the carburetor, making it easier to start the engine. Take a moment to look at the components of the carburetor. A link in the video description will take you to an interactive website where you can explore its various features. This concludes the videos on aircraft systems and descriptions.